Okay, so let's look at another question here. So let's say that we are wanting to find the shortest distance between two lines. There's various approaches that we could use. One of the things that can help is to think of a vector form of our equation. So for line one, we're going to have some point and some directional vector. And for line two, we already have it in parametric form, so it'll be a little bit easier to determine our point and our vector. Okay. So with line one, we look at our numerators. They're all in the form of x minus x naught, y minus y naught, z minus z naught. We have the directionality 3, negative 16, and 7. In parametric form, the parameter is telling us our directionality in terms of what the parameter is being multiplied by. So we've got 3, 8, and negative 5. For line 2, we have the point 15, 29, and 5. And for line 1, we've got point 8, negative 9, and 10. Okay. So there is a formula that can be memorized for the shortest distance between two lines in 3 dimensions. But one of the things that we can think of is other items that we have used, right? So we could say that, hey, maybe I have a plane, right? And within that plane is located line 2. And then I have somewhere beyond the plane, I might have line 1, right? And so then if I wanted to figure out the shortest distance between those two lines, I could be figuring out the shortest distance between line 1 and plane 2, and that's going to be on a perpendicular. And because we're going to be on a perpendicular, I'm going to want to determine the normal vector between these two lines. Right? And so my normal vector, I can find in a number of ways. I'll use the determinant approach. And so we'll have the R line 1 vector directionalities, 3, negative 16, 7. And we have the line 2 directionality, which is 3, 8, negative 5. So if I look to those, then I know that I'm going to have in the I direction or in the X direction, I'm going to have 80, and then minus 7 times 8, right? In the opposite J direction, I'm going to have 3 times negative 5, which is 15, and I'm going to have 3, so 1. And then in the K direction or the Z direction, I'm going to have 3 times 8, that's going to be 24, and then minus a negative 40. Okay, so that tells me that my normal vector, is going to be 80 minus 56, opposite negative 15 minus 21. And if we look to this, we seem to have 24 plus 48, so it'd be 70. Okay, it seems like we have 12 as a common factor for these. It seems like we've got 12 as a common factor, so I could say this normal vector would be the same as 12 times 2 6. So now we have a normal vector, right? And with that normal vector, I can figure out a new line, and let's say that we're going to call this line 3, and I could basically say, let me have line 3 intersecting plane and line 1. If I know line 10 is a point on line 1, I could then use that to find the distance between this line and this plane, which is in effect how the formula for finding the distance between two lines works. So let's go ahead and define the equation for plane 2. Well, the equation for plane 2 will be 2x plus 3y plus 6z is going to be equal to, and I'll have 2, 4, 6 dotted with a point that's in plane 2. And if I do that mathematics, 15 times 2, 3 times 29 is 5. That's going to be 30 plus, let's see here, 87 plus 30. So that'll be 60 plus 87, 147. So now I have an equation for plane 2, and I can figure out the intersection between line 3 and plane 2, right? Because that intersection between line 3 and plane 2, let's say that we mark that with a P, I can find that point P, that point of intersection. And I would be able to do that by having my equation for line 3, and the point on line 3, which is that point on line 1, 8, 10. So I can have 2 times 8 plus 2 mu plus 3 times -9 plus 3 mu plus 6 times 10 plus 6 mu being equal to 147. Once again, the directionality for this line 3 is the normal vector, and that normal vector has directionality 2, 3, 6. So I could look to solve that by hand, but maybe I have a calculator that can help me solve, and so I can come over and look in my calculator and set up to solve an equation, and that was 2 times, whoops, let's correct this, that'd be 2 times 8 plus 2 and the variable plus 3 times, 3 times 10 plus 3 times the variable plus 6 times, oh no, the point was not 10 first, the point was a -9. So -9 plus 3 at the variable, and then 10 plus 6 times the variable, and that needs to be equal to 147. And we'll just double check that that is the correct equation. 2a plus 2 mu, 3 -9 plus 3 mu, 6 times 6 mu is 147. So we can come over, right, and let's go ahead and solve the equation. It tells us that our variable is 2. So what does that tell us? It tells us that mu is equal to 2, and so therefore our distance is going to be 2 times the magnitude of that normal vector, 2, 3, 6, right? Because it's going to take the normal vector being applied twice to get from this line 1 down to line 2, traveling along that normal vector, traveling along line 3. So that sets us up with 2 times the square root of 4 plus 9 plus 36, which is going to be 2 times the square root of 49, which is equal to 7. So therefore, our shortest distance between our two lines is 7 units. So once again, a quick rehash. Rather than use a formula that can be memorized between line L1 and L2, we'll go from the conceptual approach of saying if we have line L1 and we have line L2, then I know the shortest distance is going to be a perpendicular distance. Because we know a normal is perpendicular, we can find the normal vector, and then we can find this line 3. We can find this line 3 that would have the point at -9, 10, and the directionality of the normal vector. And we're going to take that line 3 and substitute it into our plane 2, where plane 2 has line 2 involved with it. So, somewhat complicated problem, but really gets to the idea of finding distances for vectors.